you guys remember what's the formulas we know? We know 2 sine theta, cosine theta is what? Sine 2 theta. How about cosine 2 theta? How do we get that? It's what? Oh, so you're going to drive it from the I mean, fine. We can work. It is true. This is what I remember. Then I always have to solve this thing for the cosine 2 theta. So cosine 2 theta is equal to 2 cosine squared theta minus 1, which is what? Oh, I guess that's kind of it, right? Okay, so let's put that. Let's think about theta equals to x over 2, right? If we do that, we have sine of x is what? Sine of 2 theta is what? That's sine of x, but what's it equal to? 2 times the sine of x over 2, right? Times the cosine of x over 2, which is just what? It's what? It's 2u over 1 plus u squared. So there's one of our important fundamental identities for the Weierstrauss substitution. We can replace sine x by 2u over 1 plus u squared if we make this fundamental u equals tangent x over 2 substitution. What about cosine x? What's that become? Cosine of 2 theta, right, is 2, cosine of 2 theta is cosine x, right? But it's also 2 cosine squared x over 2 minus 1, which is what? We have cosine x over 2 over there, right? So we got 2 over what? Over 1 plus u squared minus 1. Can we simplify that? Let's make a common denominator. We have what? 2 minus 1 plus u squared parentheses divided by 1 plus u squared, which is just what? Cosine of x is equal to 1 minus u squared over 1 plus u squared. And now we're off to the races. Well, I guess one other thing. How is du and dx related? We're also going to need to change the measure. If you calculate du, we got what? Du is secant squared x over 2 dx, which is what? Dx over cosine squared x over 2, right? Which is just what? Looking at this, that's what? One over 1 plus u squared, right? So therefore, let's see here. So what I have is one more step. Du is 1 plus u squared times dx, right? So therefore dx is equal to du over 1 plus u squared. There you go. I think now we have all the toys we need to play the game of Weierstrauss. All right? Those are the fundamental building blocks of the Weierstrauss substitution. Let's see here. So we can take it out for a spin now, see how it works. Let's try out, I don't know. Actually, if I have any sense, I probably should look at the book and make sure I pick out an example which isn't too hideous. No, fine. I'll do example 4 in the book. 1 over 3 sine x minus 4 cosine x. You know what? I'm gonna live life less traveled. I'm not gonna do the book example. Let's try out sine x plus cosine x. Now this one you could do without a Weierstrauss substitution, but I'm just gonna do it this way, just for fun. So if we use the Weierstrauss substitution, what we do is we, like I wrote over there, make those substitutions. So what do we have? What's dx? du over 1 plus u squared, right? That's my dx to start with. Now I've got what? What was sine x? We worked it out. It was 2u over 1 plus u squared. What was cosine x? 1 minus u squared over 1 plus u squared. Do you see how that simplifies? What happens if we multiply? What should we do to simplify this? How can we clear out the denominators in the top and the bottom? And is anything lost by making this step? I'm multiplying by something which is clearly non-negative. I mean, it's clearly positive, more to the point. So that there's nothing lost in multiplying by that. What happens when I do that? Yeah. So let's factor out a minus to make life easier. So this is what, u squared minus 2u minus 1. Oh, unpleasant. Ugh. So how do you integrate this? Right? Completing the square. Oh. This is why you should do book examples. Oh. Well, I mean, it is what it is. So I'm facing the problem 1 over, I'm going to leave the minus there, u squared minus 2u minus 1. This is really something like a over u minus 1 minus the square root of 2 plus b over u minus 1 plus the square root of 2. See, because this factors. Right? Unpleasant, but true. And so, usual partial fractions, what do I get? Now, if you call this thing Pac-Man, per my custom, then if you let Pac-Man eat 1 minus the square root of 2, what do you get? 1 is equal to what? That makes this term go away, right? This one survives, we get what? So therefore b is minus 1 over 2 root 2. And if you let Pac-Man eat the other root, 1 plus the square root of 2, that gives me 1 is equal to a. And then this time I get the 1's cancel again, and you get 2 root 2 again. So a is equal to 1 over 2 root 2. And sorry, I've worked myself out of space here. So we have then is 1 over 2 root 2, and then we've got 1 over u minus 1 minus root 2 minus 1 over u minus 1 plus root 2 du, which of course you can integrate, right? I mean, it's 1 over 2 root 2, parentheses, natural log of the absolute value. If you don't mind, I'm going to put back what u was. What's u? Tangent x over 2 minus 1 minus square root of 2 minus the natural log of the absolute value of the tangent of x over 2 minus 1 plus the square root of 2, close absolute value plus constant. And I imagine that this expression could be simplified, but I also imagine that you also have other classes to go to. So, oh, thank you. Yeah, I forgot my minus issue. So you're absolutely right. So there's a minus here, which I'll make green, and that was neglected in the partial fractions, but the integration has to include it, right? So I put a minus here, and then we're good, right? Is it? No, that right. Sorry, this example is kind of ugly. If I choose the right numbers in front of sine and cosine when I make this step, I can end up with something that doesn't have such a hideous partial fractions decomposition. Like the one in your book, if you look at example 4, it works out to like partial fractions with integers rather than roots. But at some point you guys want to solve real world problems, and real world problems don't come with integers. They come with ugly decimal yucky stuff, which to us appears as square root of 2, but to you would appear as 1.414 blah, 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 blah. Anyway, I shut up. I'll see you guys tomorrow.